All right, let's see. Oh, yeah. Well, got to get Airtame back now. Shoot. 680. All right, finally. Yeah, sorry for this delay that we run into recording these lectures every time. It seems that there's always a few more buttons to push, a little bit more to work through before we can actually get going. Anyway, this is the lecture for Friday, March the 5th, 2021. Okay. So as far as the announcements go, finish up chapter 16b. This is the end of the equilibrium chapter. We are going to beginning acids and bases today. So, lab 4, yeah, we're done with the thermodynamics lab. Next week is the kinetics lab. So we're back to the regular lab manual for next week. And make sure that you do lab 5 for your preparation. Don't forget worksheet 12 is due today, and the exam is coming up next week. A little despair. Inside every snowflake is a perfectly unique meltdown just waiting to happen. Ooh, a friend is just a stranger you haven't alienated yet. Choose a job that you love and you'll never have to work a day in your life. We're sending those jobs elsewhere. You'll always miss 100% of the shots you don't take, and statistically speaking, 99% of the shots you do. You aren't being paid to believe in the power of your dreams. Oof. At some point, hanging in there just makes you look like an even bigger loser. And finally, it's best to avoid standing directly between a competitive jerk and his goals. So today we're going to finish equilibrium. There are a couple of more problems that I want to wrap up. And we will then move into acids and bases. We spent some time talking about, in our last lecture, talking about this reaction where we have hydrogen and fluorine going to HF. We started with this concentration of the hydrogen and the fluorine, and the reaction shifted right, and we could calculate the concentrations at equilibrium of everything, and we did that. We also looked at the case where we had the same reaction, same equilibrium constant, but now instead of starting with 0.258 molar hydrogen and fluorine, we're starting with 0.258 molar HF. The reaction shifts left, and we can calculate the equilibrium concentrations that way. Now, before we go take the next step here, we need to talk about the reaction quotient. The reaction quotient is called Q. Q has the exact same form as the equilibrium constant expression. The Q expression is the same as the K expression, but the system isn't necessarily at equilibrium. So if we're talking about K, the system has to be balanced at equilibrium. In the case of Q, it looks like it, but it doesn't have to be at equilibrium. If Q and K are the same numerically, then the reaction's at equilibrium. If Q is less than K, the reaction shifts right to reach equilibrium. If Q is greater than K, the reaction shifts left to reach equilibrium. So Q simply tells us the position of the equilibrium. Do we need to shift left or do we need to shift right? And here's an example. So let's take a look at, again, this same reaction. But what we're going to do this time is determine whether it's at equilibrium or not. Now, let's see. For this particular reaction, we know the value of K, so let's solve for Q. Q is equal to HF, concentration, squared, all over H F. So it looks like this. 0.258. Everything is 0.258. So this is 0. Squared all over 0.258 times 0.258, so that's squared, equals 1. Q is 1. Q is less than K. So what does that mean? It means that our denominator is too small, and our numerator, it's too small, and our numerator is too big. Is that right? No. What it means is that this is too big, the denominator is too big, and the numerator is too small. 1 is less than 389, which is our value of K. So because Q is much less than K, the reaction is going to shift from reactants to products. Remember, this is products over reactants. The reaction will shift in this direction to make more of this until we reach equilibrium. So the reaction shifts from left to right. I'm just going to go down here, like I did before, and do the ICE table. The question is, determine the equilibrium concentrations of each species given. Equilibrium concentrations. So initially, we have 0.258. For fluorine, it's 0.258. And for HF, 0.25. So we have all of our starting concentrations. Because Q is less than K, the reaction shifts right. We know that. So that means that we lose X, and we gain 2X. Don't forget the 2. We gain 2X. How do we know this is minus X instead of plus X? Because Q is less than K, the reaction shifts right in order to reach equilibrium. So at equilibrium, we have 0.258 minus X, 0.258 plus 2X. Now, we solve for X. 389 is equal to 0.258 plus 2X squared all over 0.258 minus X. 0.258 minus X squared. Squared number. We can just do the square root of both sides. And what we have is the square root of 398 or 389 is equal to 0.258 plus 2X all over 0.258 minus X. Be careful that you don't lose the 2X above, and this is not the same. It's just minus X. All right, so let's see the square root of 389. I should probably know this, but I don't right off the bat. Come on. It's one of these. Here it is. 389 square root 19.7. 19.7 is equal to 258, 5.09. So I am going to subtract 0.258 from both sides. 4.83. And then I'm going to add 19.7x to both sides. So this becomes 21.7. 0.223. X is equal to 0.223. That makes sense. X is smaller than 0.258. So we subtract 0.223 and this becomes 0.035. 2 times this is 0.446. We add 0.446 and 0.258, and we have 0.68 is 14, 5 and 5 is 10. This is going to be 7.704. So the reaction, the equilibrium, lies fairly far to the right. Notice that our K value at 389, our K value at 389 means that this particular reaction favors the products. This is how we determine which way the reaction shifts. And we can calculate our equilibrium concentrations of each thing by finding how far it shifts in terms of X. Places where people make mistakes, right here, this thing right here, or this thing right here. Okay. How to use ice tables? Okay, what if we didn't get this right? What if we said, yeah, it doesn't shift right, it shifts left? So what if we had this as minus 2x, plus x, and plus x? If we had the signs reversed, then x would be a negative value, and then this would be minus a negative, it would end up plus. So you would end up working it out the same way. But it is important to recognize how Q compares to K and which way this is going to shift if it's not in equilibrium. And that's how we use Q. Here's one more question. I'm going to erase this. And then we're going to switch markers because this black isn't holding up too, isn't holding up too well. Now, the numbers that we have, I'm just going to write these up above. So if an additional 1.21 molar of HF is added to the equilibrium system from the last problem, this is the equilibrium system from the last problem. So H2, F2, 2HI. This number is 0.035, 0.035, 0.704. So we have those. And now the question is, we had 1.21 molar of HF to this system right here. If we had 1.21 molar, we're increasing this number by 1.21. Increasing this concentration is going to shift it back to the left. So instead of having 0.704, this becomes 1.914. And I'll just keep that last 4 for now. We know that this number, under these conditions, 1.914, the reaction is going to shift to the left. Plus x and plus x. So now we just do that equilibrium problem all over again. It's pretty easy to do. This minus 2x, this and this. So the numbers that we ended up with, we now added the 1.21 to the product. We know it's forcing this to the left because it was at equilibrium with the 0.70 whatever. So now we end up having our new equilibrium conditions. And we plug it in. So square root of, I'm going to take a shortcut here. So the square root of 389, which is 19.7, is equal to 1.914 minus 2x all over 0.035 plus x. This was squared. This whole thing is squared. This is squared. So in the equilibrium constant expression, this was squared over this times this, which is squared. I just bypassed that step because we've seen it 3 times now. Take the square root, I end up with this equal to the square root of 389. Okay. 19.7 times 0.035. 0.689, 0.690. I'll keep it for now. 0.6895. We can always round at the end. Plus 19.7x is equal to 1.914 minus 2x. All right. I'm going to subtract 0.6895 from both sides. We get 1.22. And then I'm going to add 2x to both sides, and this is 21.7 x. .056. So my new equilibrium concentrations, what we did is we dumped a bunch more HF in that shifted, or HF, I'm going to put an HI here for, this is HF. We added a bunch more HF, driving this to the left. How far did it drive it to the left? Well, X is this number. So our new equilibrium concentrations are 0.035 plus 0.056. That is 0.091. And 1.914 minus 2 times this is 0.112. Minus 0.112, and that is equal to 2081. 1.802. We'll call it 1.80. All right, that's how we do these problems. We add some, it shifts it. How far does it shift it? Solve for x. So these are the new equilibrium concentrations after we've added the 1.21 molar of HF. At this point, okay, we're done with equilibrium. So if an equilibrium lies far to the right, the value for K is, it'll be big quantities of products divided by smaller quantities of reactants. If the equilibrium lies far to the left, the value for K is small. If it's small, that means that our products are small numbers and our reactants are larger numbers. So small over large gives us a small number. K will never have negative values. K will not be negative. It'll be much less than 1, like 10 to the minus 10th, 10 to the minus 5th, 10 to the minus 20th. Or K can be very large, 10 to the 5th, 10 to the 10th, 10 to the 20th. And that brings us to the end of chapter 16, equilibrium. So we're totally done with equilibrium. We'll never see it again. That's wrong. We will see equilibrium very soon because we know and love equilibrium, and we just want to keep coming back to it over and over. In General Chemistry 1, we talk about acids and bases. We talk about what they are. There are a couple of definitions for acids and bases. We talk about how to name them. And in this chapter, we're going to talk about how to use them. So we'll do a quick review on acids and bases. As far as the definition of acids, the oldest definition is the Arrhenius definition. The same Arrhenius that we know and love from the Arrhenius equation. Remember, in kinetics, it was natural log of K1 over K2. The rate constants is equal to activation energy over R. And that particular equation we call the Arrhenius equation because he did a lot of work on that area. He also named acids as being compounds that produce hydrogen ion in solution. Bases produce hydroxide ion in solution. A little bit more modern definition, about 40 or 50 years later, was Bronsted and Lowry. We often just call it the Bronsted definition, the Danish O and Bronsted. Acids are hydrogen ion donors, bases are hydrogen ion acceptors. Proton, an H plus, is simply a hydrogen atom, 1 proton in the nucleus, 1 electron, without the electron. So it's often called a proton. H plus and proton are exactly the same thing. So Bronsted-Lowry is this idea of something giving an H plus to something else, which accepts it. Whatever gives the hydrogen ion is the acid, whatever accepts it is the base. So here HCl is the acid because it gives an H plus to water, giving us this. What you do is you look at the compound on the left containing chlorine and the thing on the right containing chlorine, HCl, Cl minus. The difference between these two things is an H plus. Since this gave it up, this was the acid. Water accepted it. This is the Bronsted base. Acid, conjugate base. Base, conjugate acid. This is the acid because it's what gave the hydrogen away. What we're left with at the end is the conjugate base of the acid that we started with. The difference in a conjugate acid-base pair is 1 H plus. For H2O and H3O plus, the difference is 1 H plus. This is the base form because it accepted the hydrogen ion, giving us this at the end, the conjugate acid. Naming acids. First of all, you know that acids are identified because they are compounds where hydrogen is the only cation. Hydrogen is the only cation. So all of these, for these 4, is this an acid? Yes, it is. H plus is the only cation. We have H plus and chloride ion. This has hydrogen as a cation, but it also has sodium, not the only cation. Same thing here. Here we have 2 sodium, or 1 sodium and 2 hydrogens. Is this an acid? No, these are salts. Hydrogen is not the only cation. This is an acid as well. You name it, you name acids on the basis of the anion. Any anion that ends with ATE, by the way, these are the only 3 endings for anions. ATE, ITE, and IDE. Ate, ite, and ide. And this is how you name them. Sulfate, SO4, 2 minus. You know your ions. You have to know your ions. You have to know your ions without even really thinking about it. You need to know formula, charge, name properly spelled. accurately. Name, sulfate. This should be then sulfic acid, right? Well, that comes from old times. It's called sulfuric acid. Chlorate, chloric acid. ITE, so let's say if we had chlorite, HClO2, chlorite, as an acid becomes chlorous acid, CHLOROUS acid. Finally, if it ends with IDE, as in chloride, HCl, chloride, the IDE ending, you put a hydro out front, hydrochloric acid. You remember all this. Gen Chem 1. Happy days. So here's an example of the chlorine series. Chloride, IDE, hydrochloric acid. Hypochlorite, ITE, hypochlor, same front. The ITE gets replaced by OUS acid, hypochlorous acid. Chlorite, chlorous acid. Chlorate, now the ATE goes to the ic acid, chloric. Perchlorate, perchlor stays there, perchloric acid. How to name? Practice naming these. Practice naming these. I'll go through just a couple. NO3 minus, nitrate. As an acid, this becomes nitric acid. Carbonate becomes carbonic acid. Down here, S2O3, 2 minus. What's the name of that anion? S2O3, 2 minus. Come on. Anyone? That's it. Thiosulfate. Thiosulfate. ATE ending. Thiosulfuric acid. You should be able to name the rest. The 7 strong acids. In general, there are more, but in general chemistry, these are the common ones. HCl, HBr, HI, the 3 hydrohalic acids. Then we have 2 more that contain chlorine, chloric acid and perchloric acid. Then we have nitric and sulfuric. These are the 7 strong acids, and you have to know them. You have to know that they are strong acids. There's no getting around it. It's part of that list of things you have to memorize. If you had Gen Chem 1 from me, I would make you memorize this. You have to know the 7 strong acids. The reason you have to know them is because every other acid is weak. Every other acid is weak. These are the strong bases. Notice the pattern, lithium through cesium. These are all the group 1 metal cations. These are the alkali metal cations. These are all strong bases, which means that when we take LiOH and put it in water, it completely separates into its ions. That's what strong means. This is exactly what happens with the 7 strong acids from the previous slide. When you put those strong acids into water, they 100% separate into H plus and anion. So those are strong. These are your strong bases, total separation into anions. Notice that the bottom 3 are alkaline earth metals. Barium is really the only one that's seriously used in any way. By far, by the way, of the 2 most commonly used strong bases, 99.9% of the time, NaOH and KOH. NaOH and KOH are by far the most common strong bases. Strong and weak acids. Okay, now do you remember your strong acids? Well, that's good, because now we're going to test. Strong or weak? It's a strong acid. Strong or weak? Not a strong acid, so it's weak. Strong or weak? Not one of the 7 strong ones, it is weak. Strong or weak? That's right, nitric acid is strong. Strong or weak? Name? Chloric acid. HF, strong or weak? It is not one of the 7. You have HCl, HBr, HI, but not HF. HF is weak. Down here, strong or weak base? NaOH, strong. NH3, not strong, weak. NH4OH, not one of the strong ones, weak. What about this? This is another type of base. It's these amine compounds, the nitrogen with the double bond, with the lone pair of electrons that are free. They act as bases. They accept hydrogen ions at this nitrogen. This is weak, not one of the strong ones. This is strong. How about this one? That's right, that also is strong. Okay. We're going through a little bit of this today. We're not going too far into calculations, but we are going to talk about pH. You should have seen this from General Chemistry 1. Little p in front of a chemical symbol or in front of a constant means that this is the negative log of it. Little p, negative log of. So pH, negative log of hydrogen ion concentration. POH, negative log of hydroxide ion concentration. Together, pH plus POH is equal to 14. Always. And always the case for aqueous solutions, water solutions at room temperature. If we have hydrogen ion, if we know this concentration, we can find the other 3. If we're given hydrogen ion concentration, we can find hydroxide concentration because I have a board to erase. I know that Kw I know the relationship between hydrogen and hydroxide ion is this. The Kw, this is the equilibrium constant. This is 1 times 10 to the minus 14. It is always the case for H plus times hydroxide. And it comes from this reaction. H2O is in equilibrium with H plus and OH. Excuse me. So you write the equilibrium constant expression for this reaction. Looks like this. Kw, K, it's given W for water, is equal to this concentration times this divided by liquid water. But as a liquid, this never appears. Whatever that factor is, it gets rolled into the value of K. So I can convert between hydrogen and hydroxide ion concentrations in solution. Now notice what we have here. We have an equation with only 2 variables. If hydrogen ion concentration increases, hydroxide ion concentration has to decrease, and vice versa. I can get between, I can convert between hydrogen ion concentration and pH easily by this equation, just like on the previous slide. I showed you that correlation. And pH plus POH is equal to 14.00. 14.00. If I take the negative log of this whole equation, negative log of 1 times 10 to the minus 14, the log of this number is minus 14. Change the sign. 14.00 is equal to negative log of this and plus negative log of that. So I can convert between those 2. You should be able to do these calculations quickly. If you're given pH, you can find hydrogen ion concentration. So let's say that the pH of something is let's say I give you the pH of 5.73. What is hydrogen ion concentration? Hydrogen ion concentration, well, I know that pH is equal to negative log H plus. Therefore, hydrogen ion concentration, if I just solve this equation, I see negative pH is equal to log of H plus concentration. Hydrogen ion concentration is equal to 10 to the minus pH. The pH equals negative log of hydrogen ion concentration. Hydrogen ion concentration is equal to 10 to the minus pH. These are how we interconvert between them. All right, I'm going to stop here. I think we've covered enough material for Friday, and we will pick up here on Monday. If I can figure out how to turn this off. There we go.